That's the fat, that's the bifurcated. And for the females versus males, we see a difference. So what does that tell you about that trait? Sex length. So we know the number of wings is sex length. And we see in the females, so right here, if the males, right here, if 4 wings is dominant, what should be the phenotype of all of the females? Okay, so the male's like this. So the only information he has is this, because he's from a true breeding population for 4 wings. So I don't know if it's dominant or not. And we crossed it with a female that was true breeding for 8 wings. So that means the females will be the heterozygous individual. And what do we see in the females? 4 wings. So what does that make mutation? Dominant or recessive? Okay, I'm going to do this again. Okay, we got 8 wings, which is mutation. And we have 4 wings. It's either like this, or it's uppercase like this. But I can look in the heterozygote to tell. And in the heterozygote, I see the normal phenotype, so that makes the mutation recessive. So 8 wings is lowercase. Okay? So we know the letters we should be using. Okay. Now let's look at the data. We then took an F1 female, crossed it with a male that was thin, bifurcated in 4 wings. And let's look at the data. Let's look at the traits. We already know wing is sex linked from this information. Okay? So that cross told us this. But it didn't tell us anything else with sex linked. But now let's look at this data. Let's look at thin versus fat. Thin we have 125, 150, 250, 250, 1 to 1 ratio. And in the females we see 250 to 250. So I see no difference between males and females there. So the fat allele, probably on the autosome, there's no information to ever tell me otherwise. Let's look at bifurcated versus straight. In the males we see 125 bifurcated plus 125, that's 250. And we see 125, 250 straight. So 1 to 1 ratio. Now let's look at the females. Bifurcated, 250. Bifurcated, 250. They're all bifurcated, right? So all of them are bifurcated. So what does that tell you about the bifurcated locus? Sex linked. So we now know bifurcated is on the X chromosome as well. So we did not get that information from the first cross. So sometimes not everything is revealed by a particular cross. So we now know bifurcated is sex linked. So let's go back and try to do the very original cross. So very original. So we have a male who's fat, true breeding. And then now we know X, 8 wings is sex linked. And he had 4 wings, which means he was like this. And he has straight antenna. Okay. We know this was sex linked. We saw that difference in this data. We saw this difference in the first set of data. Now, I'm going to pretend they're unlinked on the X chromosome, which can happen when traits are far enough apart on an autosome or a sex chromosome. They sort independently. And then the female was like this. She was thin. And then X-linked, and she was bifurcated, and 8 wings. So the F1 female will be heterozygous for this. And then for the X, we'll have gotten the BF EW, and the X EW plus BF plus. Again, it gets this chromosome, or this, but they're the same. It's either this or this. And if they were unlinked, let's do our predictions. And then the male here was thin. That already matched the data. And this male was bifurcated. And 4 wings. And Y. Okay. I'm going to erase, not this board, because this is what we need. So let's look at the gametes this female would make if they were genetically unlinked. They're still sex-linked. I hate the term sex-linked. All sex-linked means is on an X or a Y chromosome. One trait can be sex-linked. But to have traits genetically linked, you must have 2 traits, okay? All right, so let's look at this. If this is the genotype of the female, and please tell me if I make a mistake. I'm looking like this, trying to write it. That was already a mistake, wasn't it? So if this is sorting independently, I should make this. This is the other parental. So let's say they sort independently. Then I should make, so there's that chromosome, there's that, there's this one. So it'd be BF, EW plus, and X, BF plus, EW. If these are sorted independently, it's 1/4, 1/4, 1/4, 1/4. And the easiest place to look is in the male because the male gives the Y. So if this is the case, I should expect to find 1/4 like this, 1/4 like that, 1/4 like that, if they sort independently. So let's look. For bifurcated and 8 wings, what was the number for the males? Bifurcated and 8 wings for the males. Bifurcated and 8 is 100, and 100 is 200. So is it going to be linked or unlinked? It's going to be linked because we're already away from the ratio we would have expected. So let's look at normal and normal. So straight and 4 for the males. Straight and 4 is 100. Straight and 4 is 100. That makes 200. Let's look at this. Bifurcated and 4. Bifurcated and 4, 25. Bifurcated and 4, 25 makes 50 and 50. So it wasn't 125, 125, 125, 125. It was 200, 200. So these represent the parental chromosomes. And we didn't even need to do this because it had to be this way and this way, right? Because we were starting with true breeding. I just did this again to reinforce to show you how you could come up with the data. Right? Do you want me to go over this again? People are shaking their heads no. Okay, good. I hope that's reflective. So, all right, so if this is the case, there's 100 out of 500 offspring that have recombinant, so the map distance would be 20 map units. Okay? Now it says here, question 46, if you analyze the wing number locus using PCR, how many of the 500 female fly progeny would show 2 bands? 2 bands because they're heterozygous. So what we see here is for the wing locus, they all had 4 wings, right? They all had 4 wings. Okay? But some of these are because they're homozygous for 4 wings, others because they're heterozygous. Okay? So of those, I haven't done the number, but anyone remember what the answer is? But is it 200 or 250. Okay, so what would happen is, this was for which one? Wing locus. So in this case, the female got this from, we're still with this one, is that right? F1 female with a male bifurcated wing. So he's got to give the X, BF, BW plus. So in this case, this category would be heterozygous for the 8 wings. This category would be homozygous for the 4 wings. So this would give 1 band. This would give 2 bands. Because on PCR, that would be 1 product size, PCR, a different product size. And then here, this one would be EW plus, EW plus. That gives you 1 band. And then last here, this one is the heterozygous for that wing locus. So those 50 would produce 2 bands. So these 50 produce 2 bands because they're heterozygous for this, and these 200 produce this. These 250 here would present just 1 band. Okay? Does that kind of make sense? You need me to go over why there's 2 bands. Okay? Because it says in this case, different alleles yield different size PCR products. It says it in the question. Okay? All right. So it says specifically one allele yields one size, the other allele yields another size. So whenever it's heterozygous, which is 2 different alleles, you get 2 bands. Question. So the question is, would the single band be brighter than the double band? If PCR worked, then what would happen here is we said that we should have had 250 that gave 2 bands, 250 gave that 1 band. So indeed, the 1 band, wherever it is, would be the same, if PCR worked equally, would be the same intensity as those 2 bands. Okay, in terms of this. Since this is bigger, this might have slightly more fluorescence. So if this is, let's say, some unit, 14, this might be 7, and this might be 8 because this is a bigger size. So if you have the same number of molecules, this should be twice as many molecules here. So this should be half of that. But since this is a little bit bigger, it's going to have a little bit more fluorescence for the same number of molecules. Okay, so there's slightly more fluorescence. Okay. All right, let's move. More questions on this? Let's move on. Okay, so what question next? Let's do page 58, number 42. Okay. Could I explain the bands? Okay, so let's not do this problem. Let's do something completely different, okay? So if I have a genome like this, and I have 2 loci, these are homologous chromosomes. If this allele is the same as that, and I have my PCR primers that flank it, when I do PCR, I'm going to get so much of that size from this chromosome and so much from that size. When I run it on a gel, this is case 1. When I run it on a gel, I'll separate it and see a really band, and let's say there's 2,000 molecules there. Okay? That's case 1. This is A and A. Or let's say it's EW plus and EW plus. And now in another situation, I have a chromosome with EW plus and EW. That's what heterozygous means. And I do my PCR, I'm going to get a product there and a product here. And we got to make this one bigger. So when I run this out on a gel, I'm going to see this band that corresponds to that position, right? Because that's the EW plus information. And if everything was done in equal quantity in that, I would see 1,000 like that. Not 2,000 because I get 1,000 from this location. And let's say that's bigger. So I get 1,000 molecules like that, which represents EW. Since this is the same size, half the numbers, this will fluoresce half that. This will fluoresce slightly more because it's the same number of molecules, but it's bigger. So if I'm using bromide, it has opportunity to fluoresce more because there's more DNA there, okay? That help? Okay. And that just, okay, so now let's do this one. Page 58, number 42. I'll give you a few minutes to do that. 58, number 42. Now, I realize this may not be that useful for you if you haven't done many problems. But I'm trying to show you the technique so you can go back and do this. Which one am I doing? 58, number 42. And I've never not had a problem like this on the exam. So I'll say that again. I've never not had, or I can also say I've always had a problem like this. And the trend continues. Okay. So I'll give you a few minutes to do this problem. So go ahead and begin. Okay, I need to go over this here again because the moment I did this problem, there are a lot of questions again about this. So what I tried to do was I tried to say, if I have an individual that was homozygous like this and I did PCR, for the purposes of the teaching, I had said pretend we got 1,000 products from this, so 1,000 of this size and 1,000 from this side. So overall in that reaction there were 2,000 molecules, all the same size. So when I put it in the well and separated it, I saw 1 band of a given size, there are 2,000 molecules there. Then to show you the correlation to a heterozygous individual, I said again we do the PCR so we get 2,000 molecules present. So we got 1,000 of this and 1,000 of this. So this number here, 1,000 refers to 1,000 molecules. This number here, 1,000 refers to the number of molecules. But this piece is bigger than this because this migrated farther. Since the fluorescent is dependent upon the mass of DNA, 1,000 molecules that are bigger than 1,000 molecules here will have overall more mass, so they will fluoresce more. That's why I said there's slightly more fluorescence than here. Even though the same number of molecules, okay? All right. So now I have the problem we're trying to do here, okay? So how many will have the heterozygous genotype there? Hetero with hetero, how many have the heterozygous genotype? 1/2. That should not take you any time whatsoever. Now let's make the Punnett square. D plus, DE, parent, parent. We need a map distance, what was it? 40. So the recombinants here are going to be 0.2, 0.2. And we get D plus E and DE plus. Recombinant, recombinant. And for this one, we get DE plus is the parental, that's 0.3, 0.3, 0.3. I made this number up when I did the problem where I actually went to the lab and got data, okay? So these are just giving you 40 map units. So this is 40%, 0.2, 0.2. That means there's 60% here, 0.3, 0.3. And likewise, it's going to be linked the same in here. So now this is this parental chromosome here, 0.3, and this is the recombinant here, and this is the recombinant here. So I do want to illustrate to you that with crossings and stuff, these couplings get reassorted. So in this case, the wild types were coupled, but when they made gametes and mated, they had recombination, so we changed the coupling. So this just happens to be an example individual with a different coupling. Okay? So now we want DE over DE plus, is that correct? No, it was, yes, that's correct. So whenever I have D plus E plus, it's a no. So that's quickly out, because that's not one of the two chromosomes. This is quickly out, because it's not one of the two chromosomes. Okay, do I ever want D plus E? No, so these are out, and the D plus E here is out. So I have 4 boxes to look at. Let's see if they meet the criteria that we wanted. Does this meet? Yes or no? Yes, and that's 0.09. That's a yes. Does this meet the criteria? No, because it's D plus E, and we don't have that over here. So I'll do that with a white chalk. This is DE, DE. Does that meet our criteria? No. We got D plus, that doesn't meet our criteria. Then this is DE, D plus, that meets our criteria, and that's 0.04. So within a Punnett square, you add. So now that's 0.13, and we're done with the problem. Okay? So it doesn't really take that long to do. Just realize, if it's a simple thing like this, it's fast, right? And when you have linked genes, you may want to make the Punnett square just to see the numbers. Okay? And this Punnett square is in no way different than any Punnett square you've ever made. We just have not numbers 1, 4, 1, 4, 1, 4, 1, 4 because they are linked. Any questions about this? No? Okay, so we've done 42. Now let's do 69, number 17. So page 69, number 17. Okay. And I want to go over this because this question is actually very hard if I don't give you some background information about how to do it, okay? So we have tetraploid organisms, and the females make gametes that are 2N, and the males make haploid gametes. So, and 1N equals 12, so 4N equals 48. So what that means, in a given set, there are 12 chromosomes. So that'd be chromosome number 1, like this, chromosome number 2, like this, 3, etc., up to 12. And I'd have 4 sets. So let's look at chromosome number 1 by itself, ignoring chromosome number 2. We know that in meiosis, chromosomes assort independently, right? They line up and assort independently. So what happens to chromosome 1 does not affect chromosome number 2, right? Now, if traits are linked, that's different. But we're not talking about interlinked traits here. We're just talking about chromosomes. So let's just look at this and call this A prime, A double prime, or let's call it A1, A2, A3, and A4. And pretend those 4 alleles are all different. And somewhere along the chromosome, you're going to have differences, okay? So when we make our diploid gametes, how many of those A's does it get? 1 or 2? 2, because it's diploid. So we have, for the 2N, we have the option of A1, A2 as a possibility, A1, A3 as a possibility, A1, A4 as a possibility, A2, A3, A2, A4, and A3, A4. Those are it. There are no other possible combinations of diploid gametes for the A locus at chromosome number 1. So that means there are 6 different types for chromosome number 1. Now think back to when we did humans, and we were talking about diploids. And we said at this chromosome position, chromosome number 1, we had A and A prime, and we said there is 2 there. And on this chromosome number 2, we had B and B plus, let's say. There are 2 there. So we kept doing this, so we said we had 2 to the 23rd, where this is the possible combinations for a given chromosome, and we had 23 types. So it's 2 to the 23rd. So for the female, she can make 6 for this chromosome. How many for chromosome number 2? 6. How about chromosome number 3? 6 on down to 12. So that should be 6 raised to the 12th power for the female. The trick to see here was how you figure this out, okay? All right? Now, I thought about doing hexaploids on the exam, but it takes you way too long to figure out the number of possible ones. So hexaploids would mean 6N, you'd make gametes that are 3N, you'd figure out the A1, A2, A3, A1, A2, A4, etc. It just takes too long. Do you see how this works? Raise your hand if you don't. You don't see how that works. Okay, so do you understand that this is an A1, A2, A3, A4? Yes. And you understand that the gametes are going to have 2 of them, right? Because the gametes are half. There's from 4N to 2N. So we can either have A1 and A2, which forces the other one to have A3 and A4. So we've done A1, A2, and A3, A4. Got it? Okay, so we're done. All right? So those are the 6. Now let's do the male gametes that are haploid. What can be in that gamete? How many types can they make? 4. A1, A2, A3, or A4. So for this male, there's 4 each of the 12 positions. So this is 4 to the 12. But to get to the 4N state, we need an egg, which is 6 of the 12 possibilities, plus sperm, which is 4.